崔永安老师希望我来主持今天的 seminar. Okay, it's my great pleasure and honor to introduce Dr. Eberhard Gross. He's our Colloquian speaker today. Okay, Dr. Gross got his master's degree and also PhD from J.W. Goethe University, Frankfurt. And then 6 years later, in Germany, there's another degree called habilitation. Wendy, Legendi. Okay. So after he got his PhD, he worked in the same university as a research assistant, and then in 1984 he moved to University of California, Santa Barbara, worked as a postdoc with Nobel laureate Walter Kohn. There he worked a lot on density functional theory. And then 4 years later, or 2 years later, he got this prestigious Heisenberg fellowships and continued working in Santa Barbara. And then in 1990, he became a professor in University of Würzburg, which is a very nice town in Germany. And then in 2001, he moved to Free University Berlin, continued to be another professor in theoretical physics. Eventually, in 2009, he moved to Halle and became director of Max Planck Institute for Microstructure Physics, Halle. And this position he held until now. So you can see that he has a very big theory department over there. Sorry, probably unusual. I use slides to introduce our speaker today, but he's a bit special this time. Anyway, his research covers actually many areas of condensed matter and atomic and molecular physics. For example, superconductivity, magnetism, and the quantum source fault, as well as time-dependent phenomena in the presence of external field. His most famous work is development of time-dependent density functional theory with his famous Gross theorem, which he developed with his master student Ronch. Okay, but his latest interest is on the coupled motion of electron and the nuclear beyond Born-Oppenheimer approximation, which he will talk in a minute. But before that, let me just show you how important his time-dependent density functional theory is. You can see that in the past 10 years or so, the paper related to time-dependent density functional theory increased, like, well, at least linearly or exponentially, until, for example, last year it's more than 1,000 a year. Okay, but this density functional theory is really useful. It now has been conquered many areas of condensed matter and atomic and molecular physics. For example, optical spectrum of molecular, in green fluorescence, in photovoltaic, and also human eyes. Okay, and the time-dependent spectroscopy, like time probe spectroscopy, even plasmonic, quantum electrodynamic, and nonlinear optic, like higher harmonic generation. Okay, so this and this paper has been cited more than 5,000. Okay, because it's so useful, and his scientific achievement is really outstanding. He published more than 200 papers, book chapters, but importantly, his work has really very high impact. For example, his paper has been cited more than 23,000 times. Okay, so Now, because of his achievement, of course, he has received many honors and awards. Okay, actually, Dr. Gross demonstrated his talent already when he was a young person. He got the first prize in mathematics in Germany. So, 1971. Okay, and follow up with some other German prize. But most recent one is well, he been fellowship and professorship in many countries, like Benjamin Meek Professorship in University of Bristol, Trinity College Visiting Fellow, Slumberg Award, and also very important one is Max Planck Fellow when he was professor at the Frisch Harper Institute. And the more recent one, this is really a prestige award called Senior CMO Medal for Outstanding Scientific Achievement, which presumably the full name is in French, I just learned, so I cannot pronounce how. Anyway, that's very prestigious award. But of course, this time he's visiting Taiwan, he's receiving one of very award from our Ministry of Science and Technology, which is Du Chongming Du's Award. Okay, so this he will receive this prestige award tomorrow from our science minister. Okay, I hope I will. I don't want to take away a lot of time from Professor Gross. Okay.
Yeah, thank you very much, Professor Moore. It's a real honor and a real pleasure to be here. The topic of my talk today is not DFT, so I will report mainly about our most recent hobby, which is the coupling of electronic and nuclear motion. And it is just to be remembered that coupling of electronic and nuclear motion is something that is quite important, and there's many interesting phenomena that where this plays a role. Let me, as a motivation, just give you two examples. First is the process of vision. So the most fundamental level, there's an excitation, but an excitation of electrons. And then as a consequence of that, nuclei start moving. This is a light-induced isomerization. And then in a very complicated process that is indicated here, circular thing, the molecule that has this isomerization ultimately comes back to its original shape. Here's another example that is in the context of photovoltaics. This is a molecule, it's called triad because it consists of three separate elements, a carotene here, a porphyrin, and a buckyball. And this is discussed as a possible candidate for future solar cells. So there the idea is that you create an excitation as it's indicated here on the porphyrin by light, and then this electron-hole pair, this exciton that is created, will walk along this carotene backbone, and here typically this is fixed on a titanium dioxide surface, where then the exciton splits, and this gives you the photocurrent. Now, if you do a calculation, and this is what I'm going to show you here, with time-dependent density functional theory in real time, you fix the nuclei. This is something that you usually do as a first step, because nuclei move much more slowly than the electrons. You fix them in the first step, and then let's see what happens. So you have created this excitation here, and as I said, you were hoping that this then walks down the backbone, but you see nothing happens. And several groups in their calculations found that if you do not allow for the nuclei to move, the excitation just stays localized on the porphyrin. Now I'm going to show you another movie where you also create the excitation on the porphyrin in the beginning here. And then you see there's some motion. There's actually some very slow motion going on now. Look, this is mainly purple, but as time proceeds, this becomes more and more green. And so there is, in fact, an oscillation of charges. This is the time counter, so this is 50 femtoseconds now. And this oscillation with the oscillation time of 50 femtoseconds has actually been measured experimentally. So this is something, if you include nuclear motion, you get the proper description. If you fix the nuclei, sometimes you get totally wrong results. So this is just to serve as an observation. And now it's getting serious. So if you take that seriously, what I just said, you have to ultimately phase the full Hamiltonian of the combined system of electrons and nuclei. And this is what you see here. So we have the kinetic energy of the nuclei, shown here, kinetic energy of the electrons, and then the various interactions. So the interactions between nuclei, electron-electron interaction, and the attraction between nuclei and electrons. And then, in principle, you have to solve the full Schrödinger equation with this complete Hamiltonian. It's written down here. Or, if you want to discuss a time-dependent process, like the one that I showed you, you have to, with this Hamiltonian, include in addition the field of the light, by which you create the excitation, and then with this you have to solve the time-dependent Schrödinger equation for the complete system of electrons and nuclei. Now this is exceedingly difficult to do in practice. It's basically impossible for more than, let's say, 6 degrees of freedom. And 6 degrees of freedom is really not much, right? This is just the helium atom. So, well, you have to do some kind of approximations. And the first approximation that is usually made is the Born-Oppenheimer approximation. So you imagine, which is certainly true, nuclear motion is small as opposed to the electrons that move much faster. So in lowest order, you could say the nuclei are fixed. And then if you fix the nuclei, they don't have kinetic energy. So in the Hamiltonian that I showed you before, we just drop the kinetic energy of the nuclei, and then the nuclear coordinates just enter the rest of the Hamiltonian as parameters, not as dynamic coordinate. So we can then solve this many electron problem for each fixed nuclear set of coordinates. So this capital R with double underline is supposed to stand for the whole set of nuclear coordinates. So for each fixed nuclear coordinates, you solve this equation, and then the eigenfunctions and eigenvalues depend parametrically on the nuclear configuration. So we imagine we could solve this equation, which also we cannot, because it's many electron interactions. We cannot do this exactly, but suppose we could, then we can make this so-called adiabatic ansatz for the complete electron-nuclear wave function, where we multiply this wave function here that is now known with the nuclear wave function, and we find the best nuclear wave function by variationally optimizing it. So we plug this ansatz, remember this is known, this is already calculated, in the variation principle. We minimize with respect to this nuclear wave function, and then we get the best nuclear wave function. And I'm going to show you the equation that you get in a second. Just want to emphasize before that in this electronic problem here, you get then these eigenvalues as a function of R, so you can plot them as a function of R. And also you do not get just one, you get typically many of those so-called Born-Oppenheimer surfaces. Here I've depicted the two lowest ones. And typically they're such smooth things. And when we then get the nuclear equation of motion, typically they describe some oscillation in these wells, some nuclear vibrations. Okay, and here's now the nuclear equation. It's a nice Schrödinger equation that has these eigenvalues as a scalar potential, as an additional scalar potential, where the nuclear kinetic energy operator here acts on the subscript. So this is also a function of capital R. These two together are a scalar potential. But then in addition, there's a vector potential. So vector potential here that couples to the nuclear momentum operator. And this is a somewhat special object. It's known as Berry connection. And its definition is written down here. So we take this Born-Oppenheimer wave function, take the nuclear momentum operator, so the gradient with respect to the subscript, and then integrate out the electronic degrees of freedom. So what you're left with is a function of the nuclear coordinates, which enters this equation as a vector potential. So that's just what you get. And if you integrate that along closed path, this is called a Berry phase or a geometric phase. Now, remember I showed you on the previous transparency in this corner these smooth Born-Oppenheimer surfaces. Usually they look like these smooth things, but not always. Sometimes they look like this. So you have a lower surface that has a sharp tip here, and an upper surface that meets at exactly the same tip. So this is called a conical intersection. So this is kind of a singularity or non-analyticity, one could say. And in such a case, if these Born-Oppenheimer surfaces have that shape, then this Berry phase has a non-zero value, a non-trivial value, and is obtained by integrating around. And there's possibility of measuring this phase as it's integrated, as it's indicated here, for example, in the H3 system, shooting a hydrogen atom on the H2 molecule, and then depending if you do it that way or that way, you gather a phase difference, which might be measured. I should mention, so this concept of a geometric phase is very old. It was invented in 1956 as a very general concept by Pancharatnam, famous Indian mathematician. And in the context of quantum mechanics, this was investigated further by Michael Berry, and therefore in the context of quantum mechanics it's usually called the Berry phase. And this is the general definition of it, right? If your Hamiltonian depends on a set of parameters, and depicted here as capital R, like in Born-Oppenheimer, like in the Born-Oppenheimer Hamiltonian, the Hamiltonian depends on the nuclear coordinates as parameters. Then, with respect to parameters, you take this derivative and integrate out in this matrix element the other degrees of freedom, electronic degrees of freedom, and then take this line integral around singularity to get the Berry phase. So, and this is an important thing to remember. A non-vanishing value for this object you get only when this closed loop encircles some kind of non-analyticity, some sharp feature, some tip. Now let's just go back here. Now this sharp tip here is obtained within the Born-Oppenheimer approximation. Right? We're making an approximation. Otherwise the Hamiltonian would not depend parametrically on the coordinates. So when did I say, is this approximation valid? Well, it assumes that the nuclei move slowly compared to the motion of the electrons. So in terms of energies, this means, well, nuclei slow, electrons are fast. So the time scale of electrons is smaller than the time scale of the nuclei. And for the energies is the opposite, right? So energy scale of the electrons should be larger than the energy scale of the nuclei, which is typically the case. If you have these vibrational levels here, the energy differences are very small compared to the energy difference between the electronic Born-Oppenheimer states. However, not here, right? The electronic energy scale goes to 0. So you get this sharp feature, this conical intersection, exactly at a point in nuclear space where the Born-Oppenheimer approximation isn't valid. And so this should make you suspicious. Isn't then this whole very phase business maybe just an artifact of the Born-Oppenheimer approximation? Okay, so I'll come back to this one day. Now there is a standard way of going beyond the Born-Oppenheimer approximation, namely you expand in the complete set of Born-Oppenheimer states with time-dependent and R-dependent coefficients. So this is exact. Imagine for a while you fix this nuclear set of coordinates, right? Then with respect to the electronic Hilbert space, this is a complete system. You expand in this complete system, right? You get coefficients, and these coefficients then naturally depend on that fixed nuclear point. So this and on time. So this is formally exact. It's known as Born-Wang expansion. And then you plug this into the Schrödinger equation, and after some lines of algebra, this is what you get. First, if we had only this, it would be just a nice Schrödinger equation. Nuclear kinetic energy here and the scalar potential for this wave function. So you have a wave packet that moves in such a potential energy surface. But then, in addition, there's these so-called non-adiabatic coupling terms, first-order derivatives and second-order derivatives. And the dynamics of a molecular system is called non-adiabatic, and these terms are large, and these terms cannot be neglected. So this typically happens, and these gradients or Laplacians here are large. So when the potential energy surfaces change in space on a very small region in space, right? These avoided crossings or intersections, and so on. Okay. So now let's look at an example. So here we have two Born-Oppenheimer surfaces, right? These are the two Born-Oppenheimer wave functions that are associated with it. Those are the two energies. And then let's assume that all the other surfaces are miles away, so that in this energy regime, at least, all the other states in this complete Born-Wang expansion are unimportant. So we basically have a very good description of the complete wave function by just these two terms. Right? So this is, let's go back, these first two terms of this formally exact expansion. Okay, so we have two parts of the nuclear wave function, one could say, or two nuclear components here, one that is associated with the lone surface and one that is associated with the other surface. Okay, now let's discuss a very famous example, sodium iodine molecule, and the two lowest potential energy surfaces are depicted here. So, asymptotically, for large distances between the two atoms, this corresponds to neutral fragments, right? While this surface asymptotically corresponds to ionic fragments, while in the ground state, this is reversed. The ground state of the sodium iodide molecule, as everybody knows, this is largely ionic, and the excited state is closer to a neutral situation. Okay, so then with the laser field, you can excite, and then this wave packet that you excite here on the upper surface goes forth and back. And if this avoided crossing wouldn't be there, then this oscillation would just go forth and back forever. now, due to the presence of this avoided crossing, there's some contribution, some splitting of the wave packet that is associated with the other surface. So this is then measurable experimentally if you just measure the outcoming sodium atoms in a time probe experiment as a function of time. And so periodically, whenever this wave packet goes across the avoided crossing, then due to the non-adiabatic coupling, there's some contribution created on the other surface, which you can measure. You can easily read off the period of this oscillation. And then you can imagine you can start at higher places in this surface, so you change the frequency of the oscillation. So in this way, you can really measure this upper surface. And this is a famous experiment for which Ahmed Zubil got the Nobel Prize in 1999. So this is by now established knowledge. Everything is clear, everything is understood. So the problem is, if you want to describe this, and this is a real challenge for larger systems, because it's absolutely impossible to solve the Schrödinger equation, as I mentioned before, for more than, let's say, 6 degrees of freedom. It's also true for the nuclear Schrödinger equation. So, what do you do? Now, nuclei are in many situations largely classical. So you may not like this idea, but you actually have to make any